Okay, so again, in your book, this should be kind of like the little pre-chapter that comes before. It covers kind of measurements, significant figures, all that kind of stuff. So we're going to start with, obviously, units are really important. Whenever you take a measurement, which, as we talked about sort of earlier today, is a quantitative measurement, is actually a measurement and values, as we talked about. And again, that's different than qualitative, which is really more observations. But definitely when you take a measurement or record anything, should always have units associated with it. If I just write 100 down, what does that really mean? I could mean $100, which is really good. It could also mean maybe I got 100 apples, which may still be good, I guess, if you like apples. So really a number by itself obviously has really no reference point. The units are really important because it does give you that reference point of really what the value means. So you should always have, some type of units there, like G for grams in this particular case. Now, when we take measurements, there's always some degree of uncertainty associated with a measurement. So whenever we take a measurement, there's always a degree of uncertainty in the measurement. And really the degree of uncertainty in the measurement does depend on really the equipment that you're using. So different pieces of equipment will give you some type of different sort of degrees of uncertainty. So for example, if let's see, we'll go with, let's call that 1. Bad too. So if we had a ruler such as this, which went from 1 centimeter to 2 centimeters, and I was measuring some arrow here that I'll draw something like this. When we take a reading, there's really always 2 important things that you should look at when you are using any piece of equipment. And that's really what the major markings are on it and what the minor markings are on the sort of piece of equipment. So when we look at this sort of scale, if we start here, that is 1, and we count the dashes between it, starting with the dash after the major one. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, if you will. There are 10 markings in this case between 1 and 2 centimeters. That means each marking here, each of the smallest markings represents how much? Yeah, it represents 0.1 centimeters. This would be 1.1, right? 1.2, 1.3, 1.4, 1.5, 1.6, and so on all the way across there. Now, the biggest markings obviously are 1 centimeter. And whenever we do take a measurement, no matter who looks at it, there should always be some numbers that everybody should agree upon, no matter who takes a peek at it. Everybody that looks at this measurement here should agree upon that my arrow is at least 1.4, right? It's definitely has reached that 1.4 sort of marking. Now, when we look at the arrow, we could clearly see at this case that, it's not exactly 1.4 and it's not exactly to the 1.5 mark and so forth. And this is where really the estimation comes into play when we do take a measurement. Now, I may personally look at it and go, I think it's kind of like halfway between the 2 markings. And I would perhaps record a 5 and obviously the units with it. Somebody else may look at it and go, well, I think it's maybe hedging a little bit closer to maybe the 0.5 there. So, maybe it's like a 6 or a 7. Somebody else may say, I think it's a little closer to the other side. And that's really where the uncertainty in this measurement comes from. So what we would want to do whenever we take a measurement is we always want to make sure that we record all the certain numbers plus the first uncertain number. So whenever you take a measurement, it is always customary to record all those certain numbers plus that first uncertain number. And actually, when you do that, that is really what significant figures are. Which means in this particular case, this measurement has how many significant figures? It has 3 significant figures. All the certain numbers plus the first uncertain number is the number of significant figures that it has. So all those numbers there would be considered significant. Usually the uncertainty lies in the last significant figure. And what I said there is kind of important. It is the last significant figure. It is not always the last number that's written. So sometimes the last number written is not a significant figure, but the uncertainty is in the last significant figure. A lot of times it is the last number, but sometimes it is not always the last number. Usually you're like thinking kind of plus or minus 1 of that uncertain number is sort of where the error sort of lies within that piece of equipment. Any questions on that there? Now, it does matter, obviously, the scale that you're looking at. So, for example, if we had a wonderfully drawn graduated cylinder, you'll see why I failed art 3 times as we go through the semester here. And we got something, say, like... And let's say we have a graduated cylinder here. We're doing milliliters, and we have a liquid in there. And we'll go right about there-ish. Now, we also want to look at this scale, and we see obviously the big numbers, right, is 10 and 20. So the big difference there is 10 milliliters, right? There is, again, if we start counting at this spot right here and going to the 20, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 little markings, right? That means in this particular case, each of the little markings represent how much are the smallest markings. I guess a better way of saying that. In this case, each of the smallest markings represent 1 milliliter, right? This would be 11, this would be 12, this would be 13, 14, 15, 16, 17, 18, 19, and 20. So even though we still have the 10 markings, because of the scaling that's on this, it is obviously different than the previous 10 markings that we have. And by the way, when we do put a liquid in a glass cylinder, you always will see this curvature, exaggeratedly drawn there, of the liquid. And when we read this, this, by the way, is known as the meniscus. Yes. And you should always take a reading from the bottom of the meniscus in most cases. You want to take it from the bottom of the meniscus. And that is because when you put a liquid like water, for example, in glass, the water is actually attracted more to the glass than itself, and it actually rises on the ends as it comes up against the glass. And that's because this side is risen. Really, the true volume in there is at the bottom there that didn't rise in the middle. And that's why you read from the bottom of the meniscus in this particular case. Now, if we do that very badly here, we'll just kind of draw a straightish line there. We again can take a look at this, and there again should be certain numbers everybody agrees. And my wonderful drawing there, it is at least 15, right, in this particular case. And those would be our certain numbers. Once again, we're not exactly at 15. We're not exactly at 16. And in this case, you may hedge your bet and go, well, it kind of looks a little closer to 16 in my bad drawing. So maybe it's like 15.7 milliliters in this particular case. And this obviously would be our uncertain number. And in this particular case, this guy then would have how many significant figures? It would have 3 significant figures in this particular case, with the 7 being our uncertain number. And again, what that really means in this particular case, it could be as big as like 15.8, maybe is like somewhere maybe 15.6, there's that range. And if you look at my drawing there, that's about where we're talking about in terms of the range of where the measurement would be. Any questions on that there? Now, in most cases, you could typically go one more place to the right of the smallest marking. So what that means is, in this case, the smallest marking was 1 milliliter. We're able to go one more place to the right, which would be the first decimal place. If we look at our original guy here, the smallest marking was 0.1. We're able to go one more place to the right to give our reading. So in a lot of cases, not 100% of the time, but a lot of cases, you could go one more place to the right of the smallest marking, and you could be able to record it properly. Any questions on that there? Now, not in all cases, because you could have something like this, perhaps. All right, so now in this case, we once again, in terms of our big markings, we are looking at a difference of 10 milliliters. There's how many markings between those two in this case? There is 5, right? 1, 2, 3, 4, and 5, basically, yeah. That means each of the smallest markings in this case is actually how much? 10 divided by 5 is 2 milliliters, yeah? This would then be our 12 milliliters, 14, 16, 18. Now, when we go to take a reading of something like this, and again, we read from the bottom of the meniscus there, which would be here-ish, maybe. There we go. We are now between 14 and 16. Between 14 and 16 comes what number? 15 milliliters, right? There is not enough room between those two numbers to figure out where like 14 stops and 15 starts, right? There's not enough to visualize that difference. That means in this particular case, how many significant figures would this number have? This number would have 2 significant figures in this case. The uncertain number here would be? It would be the 5 would be our uncertain number. The 1 would be our certain number. And that means, hey, this thing could be like 16. This thing could be 14. It's somewhere in that ballpark. And that's about what we see here. So this is an example that, it may not always be able to go to one more place to the right. But I would say 9 times out of 10, you could go one more place to the right. But there are certain situations where you cannot do that. Any questions on that there? In addition, a very common thing people like to do, we'll go back to kind of like our first one there. All right, so let's just say we drew right there. So in this particular case, we once again have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 semi not evenly spaced markings there between those. So once again, each of the smallest markings is going to be 0.1 centimeters here. Once again, this would be 1.1, 1.2, 1.3, 1.4, and so forth. In this particular case, we look at my arrow and it feels like it is dead on the 1.3 mark, right? So what should I record in this case? Should I record 1.3 centimeters? Should I record 1.30 centimeters? Should I record 1.30000 centimeters? I'm going to go no with that. It just feels like a lot of zeros, just so you know. Yeah. So which one should I record? The guy on the left or the guy on the right? What's that? 1.30 would be the correct one. There is actually a difference between those two, and sometimes people don't think there's a difference between those two. And the difference comes about talking about significant figures. If we were to record this measurement here, this would have how many significant figures? Right. Which means really our uncertain number here would be the 3, right? And what we would be saying in that particular case is, I think it's 1.3, but hey, it might be 1.4 or it might be 1.2, which clearly, if we look at the picture, that guy is nowhere near those numbers, right? So by dropping off the 0 in this case, we actually made our measurement pretty crappy and worse in this case. We would want to go here because our smallest marking is to 0.1. We still have the ability to go to one more place to the right. And even if we feel it is exactly on the line, we need to preserve that measurement by adding the 0 here. So this would be the correct one. And this number would have how many significant figures? It would be 3 significant figures. All of our certain plus our first uncertain number. The 0 here would be significant. And it's significant for another reason, because if we take that measurement and we go, it's 1.30, we're basically saying, well, maybe it's 1.31 or maybe it's 1.29. And these measurements, based on what we're seeing here, is pretty realistic in what we actually see, right? Could be somewhere in that ballpark of those range. So sometimes people think, well, it's right on the nose, I'll just lop off a number. It's not that big of importance. It really is. Every time you lop off a number or don't record it properly, you're really doing crappy on your Sig Figs. And in addition, you're making your measurement a lot more uncertain, right? A lot worse of a measurement than it should be. So it's really important, and it's a very common thing that people do all the time is, frankly, they just like, I don't really need those numbers. Or for example, when they go to one of those things over there, like the balances over there, the electronical balances, and it gives you a number of like 52.325 grams. And people go, 52 seems good. And they just record like 52. You just lost a bunch of significant figures. So a couple of things. Anything that is digital, by the way, like the balances, you should always record all the numbers because they are significant and they are important. Otherwise, they wouldn't put it on the digital display. Anytime you use any type of glassware, you should always look at it and figure out what the appropriate scale is, and that you take your measurements to the appropriate scale, and also obviously put the units with them as well. Again, if you kind of get rid of some numbers, you're really making your measurement a lot worse than it should be. Any questions on how to properly take a measurement here? No? All right, so that's measurements. So that's good. We'll lead into some official Sig Fig talks. So there are ways that we could count significant figures. And by the way, there's really kind of two types of numbers, that we come with. Figures here. There are measured numbers, and they're what are referred to as exact numbers. And exact numbers are numbers where there's really no measurement involved. So for example, if I had 3 apples on my desk here, I wouldn't do any type of experiment to figure out how many apples I have. I would simply count them. And that's an exact number. Another place that we'll see a lot of exact numbers is in definitions, like, there's 12 inches in 1 foot. There's 2.54 centimeters in 1 inch. Any type of definition like that is considered exact numbers. Anything where you sort of obviously do any type of measurement, a quantitative type measurement, is obviously a measured value. So when we look at significant figures, there are certain rules that we use to count significant figures. The first rule is any non-zero number is significant. And by the way, that is pretty much where you start counting. Always when you're trying to figure out significant figures, you always start with the very first non-zero number going left to right, right? So if we had something like 1, 2, 3, 4, very creative here, we would start counting right there at number 1. Everybody else is a non-zero. This guy obviously would have 4 significant figures in this case. The uncertain number here would actually be the 4 in my measurement here, if this was a measurement. The second things that we look at are zeros, and these are sometimes the ones that give people sort of the hardest time in counting significant figures. The first type of zero that we come across is what is sometimes referred to as a leading zero, and those are not significant. So, you know, if I had 0.0000235, how many significant figures would we have in this case? We would have 3 significant figures. We would start going this way, and we wouldn't start counting until we hit the 2 that's right there. That would be 1, 2, and 3 significant figures here for this particular number. You can have as many zeros as you want. You do not start counting until you hit the very first non-zero number. The next type of zero are what are sometimes referred to as sort of trapped zeros or captive zeros. And those are significant. And I'll go up higher so it'll be easier to see. So if we had something like 4003, this guy would have 4 significant figures. We would start counting right there. The 2 zeros in the middle are significant, and our guy at the end there obviously is a non-zero, so that would be significant as well. So it would have 4 significant figures. Questions on that one there? Now, probably the zero that gives people the hardest sort of time is actually the trailing zero. And those may or may not be significant. And what determines whether or not they are significant or not is they will become significant if there is a decimal. Point in the number. Now, the decimal point just needs to be simply in the number. It doesn't need to be near the zeros. It just needs to be present. So if I had something like 12,000, like that, how many significant figures would it have? It would have 4. We would start counting here. These are the zeros at the end. There is a decimal there, makes them significant. This would have 4 significant figures. If I did 1200 like this, how much would it have? It would have only 2. As we would go to here, we would look at this. There is no decimal point written in this measurement, and it would have only 2 significant figures. In the very top one, which one is the uncertain number or the estimated number? It is this 0 right here. In the bottom one, which one is the uncertain or estimated digit? It is the 2. So this is what I was talking about earlier. Not in 100% of the time is it always the last digit that is written. It is always the last significant figure that is written. And in the case of the bottom one, the 2 is the last significant figure is written. In the case of the bottom one, that is saying, I think my measurement is 1200, but maybe it's like 1300 or 1100, right? In the top one, it is saying, you know, my measurement is like 1201 maybe, or maybe it's 1199. Which one's the better measurement? Which one has the less uncertainty? The top one has a lot less uncertainty, right? So if you have the ability to do that, you would want to take the top one. It gives you a much better measurement, right, than the bottom one. And if you weren't paying attention, you just left a decimal off or dropped off some zeros, you obviously made your number a lot worse in terms of measurement. Any questions on counting significant figures? By the way, when we write a number in scientific notation, which is n times 10 to the n. By the way, that's first n is a number between 1 and 2. 1 and 2, no, that's not right. 1 and 10, that's better. That seems like a very small number. This n up here is a positive or negative number, depending on which way you move the decimal point. So for example, if we wanted to turn this guy into scientific notation, to get me to a number between 1 and 10. By the way, that is between 1 and 10. That is not 10, 20, 100 or below. You need to go 1, 2, 3 places to the right, to the left. I'll learn left and right here. And that would turn it into 1.200 times 10 to the 1, 2, and 3. If I wanted to turn this number into scientific notation, it would be 1.2 times 10 to the 3. First off, what is the difference in the value of each of these? Difference in the value is nothing. They're both the same, 1200, right? But there is a difference in the number of significant figures, right? And whenever you write a number in scientific notation, all of the numbers that come before the times 10 part are significant. So when I write it like the top number here, that has still 4 significant figures, which is what the original number had, and we should still maintain it. When I write this guy here, it is just the 1.2 that is before the times 10 part, which is 2 significant figures, which again is what our original number should have. So if you decide to write something in scientific notation, our decimal point, you shouldn't again lose any significant figures. The benefit of scientific notation is, frankly, you could control how many significant figures you need. If I needed 3 significant figures, I could simply just write 1.20 times 10 to the 3, and you could kind of get the right number of significant figures. So sometimes the only way to report an answer to the correct number of significant figures is you might have to write it in scientific notation to do so. And again, you could control it, pretty easily that way. Any questions on that there? Now, by the way, while we're talking about scientific notation, if we'd had this number here. All right, you write in correct scientific notation. We would start here. This is all leading zeros, leading zeros. We really shouldn't start counting until we get to our first non-zero, which would be that guy. This 0 is trapped, which means it's significant. That is significant. This is also trapped, which is significant. That is significant. Is the 0 at the end significant? The 0 at the end is significant because way over here, there's a decimal point in it. It does not need to be near it. So this would have 1, 2, 3, 4, 5, 6, I think. Yeah. 6 significant figures, which means when I go to write this into scientific notation, I need to go to the right 1 place, 2 places, and 3 places, giving me 3.04050 times 10 to the minus 3, negative because I went to the right. Positive exponent, large number, right? Negative exponent, small number. So that's a way to remember it as you go that way. This again still maintains my 6 significant figures when I translated it over into our scientific notation. Question on that one there. More importantly, while we kind of diverge here to scientific notation, let's talk about scientific notation and calculators. People do not know how to type in scientific notation a lot of times properly into your calculator. Every calculator that you have should probably have a dedicated exponent button. It should have an EE button. It should have a EXP button. And if you have some of the newer ones, it will actually have a times 10 to the n type button. And if you have that calculator, I'm sorry, but we'll talk about you in just a second. So these are your exponent buttons, and you should use them when you type something in your calculator into scientific notation. If you are hitting like the multiplication button, the shift log button, you are putting it in incorrectly. So you should use these numbers correctly. So if you had something like 6.022 times 10 to the 23, and you wanted to type that into your calculator correctly, you should type 6.022. Oops, 22. There we go. You then should hit the exponent button. So you should hit the E button or the EXP button. And what the buttons represent is the times 10 part of the number. That means that you do not need to hit the multiplication button. You do not need to hit anything else other than that exponent button. On your calculator, it will usually pop up 1 of 2 ways. It will go 6.022 and maybe put an E there. and that E stands for the times 10 part of the number. Some people's calculators will go like 6.022, maybe pop up a couple of zeros up on top, maybe a times 10 on the bottom. And once you hit that, that is your exponent button. All that's left in our case is actually just the type 23. And it'll end up like this. This guy will then change to a 23. And that is the proper way to punch it into your calculator. If you had a negative exponent, like 4.25 times 10 to the negative 4, you would do the same thing. 4.25, you would hit your exponent button. You would actually hit your negative button, which all calculators have. It is not your subtract button. Usually a button like that or a button like that is your negative button there, plus and a minus. And then you would hit 4. And once again, it will pop up like 4.25 and E minus 4, or like a 4.25, and it'll do like a minus 4 up on top. So that is the proper way to punch it into your calculator. You should not be using the second or shift button. You should never be using the log button to do this. And you should never hit the multiplication button unless you're multiplying two numbers together. But you should not be hitting the multiplication button to actually put something in scientific notation. If you find yourself putting these numbers in and you're like, what will usually happen is your answer in the front part will look good, but the exponent will be off by a little bit. And that's usually an indication that you are punching it incorrectly. Now, those that have maybe some of the newer calculators that have actually this button here, what you need to do is just an extra sort of step based on the way your calculators are programmed. You need to get some place to write here. So let's just say you were doing this number and you have this button here. You would do the same thing. You would go, actually you would actually need to start with a parentheses first. You need to then go 4.25, then hit that number, the times 10 part. When you do that on that calculator, it will look something like this, 4.25 times 10, and then you'll have your little cursor bouncing up on top there. Then you would finish it out the same way. You would do your negative button and then your 4, and it will change that bouncing cursor to 4.25. Actually, you have parentheses like that. Times 10 to the minus 4. You will then have your cursor still up here on top, which is problematic. Most of those people that have that button also has a little wheel on the button on the calculator. That looks something like that. You hit this side, that brings your cursor down, and you can then close the parentheses at that point, and your number should end up looking something like this with your little cursor bouncing around on the bottom at that point. So if you do have that sort of button, which is on some of the newer calculators, most of those are programmed, I'll just say pretty crappily, yes, and not great for our applications. And if you do not put the parentheses around it, you will be in trouble because it will do the wrong math. It will do the wrong math for you. If you have the EE button or the EXP, you don't need to put parentheses around anything. You just roll it right through and you're all good. But if you do have one of those guys, you do need to make sure you need to do that. Any questions on that there? So why don't we try a couple, just make sure our calculators work here. Why don't we do 4.2 times 10 to the minus 4, and we'll divide it by 3.25 times 10 to the 6. And then let's do 3.2 times 10 to the minus 11 times 1.25 times 10 to the, we'll do 23. I'll do it as well since I made up these numbers. We'll see how we do. Okay, let's take a look. So once again, if you want to punch this in properly to your computer, I guess there are computers. We'll do this one first. You should, again, go 4.2. You should hit your exponent button. You should hit your negative button. You should then hit 4. You should hit your divide button. 3.25, exponent button, and 6, and a little equal action there. Obviously, if you had that other button that we just talked about, you need to put some parentheses around everybody there when you're doing it. 4.2 exponent, -4 divided by 3.25 exponent 6. Going to give you 1 point, I'll call it 3 times 10 to the minus 10 in this particular case. Any questions on that one there? By the way, something else people oftentimes forget is on your calculator, don't forget the exponent part. Yeah, it's on the far right there. Sometimes people will just put the front part of the number and stuff. Now, if you did this, by the way, it was like 1.292307, a whole bunch of numbers. I just rounded a little bit. If you have this number right, but this number is incorrect, it is probably how you are putting it into your calculator and stuff like that. Let's try the second one there. Same way, we're going to do 3.2. We're going to hit our exponent button, nothing else, no multiplication button. Negative button on 11. We're going to multiply it by 1.25 exponent button and a 23. Going to give us something for this guy of like 4, we'll call it 4.0 times 10 to the 12 in this case. Any question on scientific notation in your calculator? By the way, your calculator may not give you an answer in scientific notation. You don't necessarily have to give every answer in scientific notation. You can if you want, but you don't have to, unless it obviously asks you to do so. And as I mentioned earlier, sometimes the only way to get it to sort of the right number of significant figures is to use scientific notation. So sometimes you are kind of forced to do it, but you don't have to give it. You just have to give everybody to the right number of significant figures when you give an answer. Any questions on scientific notation here? So speaking of giving it to the right number of significant figures, most of the time we deal with significant figures when we're doing calculations. So let's talk about the rules when we do calculations that involve significant figures. So calculations with Sig Figs. So there's really kind of two things that we do, or two groups of things that we do. We usually either multiply or divide, or we add or subtract. So if we are doing any type of operation where we're multiplying or dividing, the answer should have the same number of Sig Figs as the number with the least number of significant figures. So the guy with the worst number of significant figures is frankly your worst measurement. So your calculation is only as good as your worst measurement. So it's kind of like, you know, the weakest link, right? You're only as good as your weakest link. So your worst measurement is as good as your calculation is going to get. So if we took 4.25 times 1.0, and we do that, I could do that in my head. Good choice. On my calculator, I get 4.25. I should record this as 4.25. Is that right? How many significant figures does this number have? 3. How many significant figures does this number have? 2. This means this guy should end up with 2 significant figures, right? The least number. That means we should round this to 4.3 would be the proper way to record that to the correct number of significant figures. Question on that there. When we add and subtract, it's a little bit different. The answer should have the same number of decimal places as the number with the least number of decimal places. So it's always the smallest number. Decimal places are a significant figure. Here we are looking at decimal places, not significant figures. So if I took 1.250 added to 2.00 added to 1.3, and give it the old college try here. That is a 0. That's a 5. That's another 5. Look at that. That's a 2, 3, 4. So I get 4.550 on this guy. 4.550 on my calculator. We are looking here at decimal places, not significant figures. So this guy's got 3 decimal places. This guy's got 2 decimal places. This guy has 1 decimal place. That means my answer actually should go to the first decimal place. That is a 5 next to it, which means I need to round up. And that gives me 4.6 should be my answer here. 4.6 has 1 decimal place. How many significant figures does it have? 2. So don't get those 2 things confused. Yeah. Question on that there. So multiplying, dividing, it is the least number of significant figures is what your answer should have. Adding and subtracting, it is the least number of decimal places. Now, if you combine or are doing multiple sort of steps along the way, you should keep track of your significant figures. And truthfully, you really should clean it up at the end and not do a lot of rounding in between. If you're doing multiple calculations where you get an answer, take it, and then do another calculation, get an answer, do another one, you want to really avoid rounding to the very end, because every time you round, you will move yourself further away from the correct answer as you do it. But you should definitely keep track of everything along the way. So if we did something like, 1.235 times 3.22 divided by 14368. Now, if we were going to do this, the first thing that we typically would do, right, is the stuff in the parentheses. And in the parentheses here, we are multiplying, which means we should be looking at significant figures here. And on the top, we have 4 significant figures for this guy. We have 3 significant figures for this guy, which means technically when we get an answer for the top part, it should have 3 significant figures, right? The next thing that we would do to complete the calculation would be to take the top number and divide it by the bottom number, which once again, we would look at significant figures. And this guy has 5 significant figures. That means we're dividing 3 significant figures by 5 significant figures. The answer should end up with 3 significant figures. So you do want to kind of keep track of it along the way. And again, I personally went around to the very end and just kind of clean it up at the end, but you should keep track of it. Also, same deal if you were doing something like this, 1.235 times 3.22 plus 4.2, something like this. So the first thing, once again, we would do is sort of this. And in this case, it would be, if I put it in there, let's see how I did on my numbers, 1.235, 3.22. That gives us technically something like 3.9767 on our calculator, which really should be rounded to 3 significant figures like we talked about before, which would take us to here. And in this case, you might want to round it since we're going to be adding it to the next number, right? Now, when we add these 2 numbers together, gives us 8.18. The correct answer should actually only be 8.2 in this case. The last thing we did was adding, right? Which we look at decimal places, which technically is 2 and 1. And we should end up with 1 decimal place, which means this guy has 1 significant figure. So, sometimes we obviously do mix and match, the operations that we're doing. You want to definitely kind of keep track of it along the way. I think, honestly, if you even just didn't round and added the 4.2, you would get something pretty close to that at the end. Any questions on calculations involving significant figures here? Now, speaking of rounding, we do not ever want to kind of do weird rounding. Rounding rules of normalness apply, right? So if it's 5 or above, we round up, right? The next number is 5 or above, we round up. If it's less than that, then obviously we just drop the rest of the numbers as to what we do. But we never want to do anything kind of crazy, So for example, if I had 13,333 and I wanted to round to 2 significant figures, what should the answer be here? Is it 13? Is it 13,000? Is it 13,000 dot? What do we think? Well, let's take a look. We'll start with this one. How many significant figures is this? It is 2 significant figures. So, hey, we're happy, right? Now, the problem with that number is if I owed you $13,333 and I said, hey, I'm going to give you 2 significant figures, here's $13. I'm probably not going to make it out of the room, right? You're not going to give me that much of a discount. So although we did hit the correct number of significant figures, we definitely changed the meaning of that number. There's a very big difference between 13,000 and 13, and you never ever want to do that. It turns your smile into an unhappy face. So we would not want to do that because clearly we changed the value of it, even though it is the right number of significant figures. This guy would have how many significant figures based on what I wrote? 5, right? Those zeros would be significant because of the decimal, which means that is definitely not 2 significant figures, right? This guy would have how many significant figures? It would have 2 significant figures. And 13,333 is pretty much the same meaning. So maybe if I give you $13,000, you give me the $333 teacher discount, and we're all good on that, and it wouldn't be too much of a problem. So sometimes people, in an effort to get the correct number of significant figures, do what I like to call extreme rounding, and they just like drop off the numbers. But you never ever want to change the meaning of the number when you are sort of rounding. And again, I would wait to round to the very end. Any questions on any of that there? I'm going to pick up a few more topics to sort of talk about, make sure, again, everybody is hopefully on the same page. But before we continue, any questions on anything we talked about so far? Everybody okay? All right. So we've been talking sort of about measurements and taking measurements properly and significant figures, obviously, and significant figures with calculations. A couple of phrases which are important in terms of measurements is accuracy and precision. There you go, precision. Now, if something is accurate, what that means is the value is close to the true value. Here. So if you have an accurate value, high accuracy, it means that you are very close to what the true value should be. Precision, on the other hand, is a group of numbers that are close to each other. So precision talks about really a group of measurements and how close they are really to each other. Accuracy is, how good you did. Precision is really kind of like how repeatable, for example, an experiment is. Sometimes you do an experiment 3 times, right? And you see if you come up with sort of the same results every single time that you do it. That's a measure of precision. So for example, if we threw some darts at a dartboard there, the goal there is to get the bullseye. And I throw my darts and I go, all right, so I missed the board. It happens, right? Am I very precise? No. Am I very accurate? I am not, right? I'm all over the place here. So, what happens? You go, hey, we'll do double or nothing. Why not, right? Give it a good old try there. So I pick up my darts. I throw them again. Am I very accurate? I am not, right? True value is bullseye in the middle. Am I very precise? I am. I'm precisely not accurate, right? So you could repeat the same experiment multiple times and do it crappy every single time the same way, right? And end up with the same type of numbers, but they may not be very accurate in that case. So I go, all right, we'll go like triple or nothing. Nobody does triple or nothing these days. We'll go triple or nothing. I pick up my darts and I throw them again here. Am I accurate? I am. Am I precise? Yeah. So usually, if you have a pretty good degree of accuracy, it might be pretty precise. but you definitely could be very precise and not very accurate. So there is a difference between those things. As I mentioned before, sometimes you will have, I guess I erased the accuracy there. Sometimes you will have an actual number or a true value, and a lot of times we will calculate something known as percent error. Percent error tells us really how accurate we are. And in terms of precision, sometimes we'll do percent deviation or percent standard deviation, and that's something that looks at precision. Any question on the difference between those two numbers there? All right, by the way, percent error, you typically want a very low number, right? High number, percent error means not such a great day for you in the lab, is usually that deal. All right, so we've been talking about units as well a little bit, but just so everybody understands, there really are sort of two types of units that we come across here. There's the English units, which we use here in the US, and pretty much everybody else in the world uses the metric system, pretty much. And obviously that creates a problem, right, as everybody does business with everybody all around the world. So in the 60s, they sort of came up with, really it's a version of the metric system, which we use a lot in chemistry and sciences. It's sometimes referred to as the SI system of units. It's the International System of Units. It's really based off of the metric system. So sometimes in chemistry, you'll see the SI unit is this or something like that. And that's sort of the standardized unit that's used in sort of chemistry and science. A lot of times when we use something like the metric system, sometimes we have really large values, sometimes we have really small values, and we sometimes have to use prefixes, right, to sort of change those things. Like kilo is 10 to the 3, centi is 10 to the minus 2, nano 10 to the minus 9, right? And when we use these prefixes to change the meaning of a value or to do a conversion, it is very common that people always screw up on these conversions here when they try to use them. So when you see something like this on a table, what these numbers represent is how much there are in the base unit to one of the prefix units. So what that means, if I am looking between grams and kilograms, I would go to this table and see kilo is 10 to the 3. That means that there are 10 to the 3 grams in 1 kilogram, not the other way around. It's very common people do it the opposite way. 10 to the 3 kilograms is 1 gram. This is the base unit, grams, right? Is the base unit for everybody there. So those are grams. And kilo is the prefix unit. So when you see those things, it's one of the prefix unit is one of the base unit. It doesn't matter what the base unit is. There would be 10 to the 3 liters in 1 kiloliter, right? There would be 10 to the 3 meters in 1 kilometer. Doesn't matter what the base unit is. The prefix stays the same. The conversion stays the same. But it is a super common mistake that people do. 1 gram is 10 to the 3 kilograms. They do that backwards. So you don't want to do it that way. That means, for example, if I had 1 nanometer, that would be 10 to the minus 9 meters. Yes. So that's, again, a super common error that people make a lot. By the way, if you needed to type that into your calculator, that is 1 times 10 to the 3, 1 times 10 to the minus 9 is how you would do it in scientific notation. If you have a calculator where you have the EE button, you could actually just hit the EE button and the exponent part without the 1, and you should be fine as well. So that's how you would put those in. Any question on those guys there? So a whole list of prefixes, milli, right, 10 to the minus 3. And again, it's super common mistake. People always get those guys kind of inverse, so you don't want to do that. Any questions on that there? Speaking of conversions, when we do calculations in chemistry, we do want to do them using do it in a way that's known as dimensional analysis. Dimensional analysis is a way where if we have a conversion factor, like let's just say unit A equals unit B. From anything like this is what is known as an equality. An equality are two guys that are on different scales but represent the same amount of something, like 100 pennies is equal to $1, right? That's an equality. From any equality, you can write conversion factors. So for example, you could write 100 pennies over $1, or you could write $1 over 100 pennies. These are conversion factors. When we do something in dimensional analysis, we show the calculation with the units and them canceling out, and we treat it like fractions, basically. So if I had, we'll go with $6, and I want to know how many pennies that was. You need to show it correctly using dimensional analysis. So we would start with what is given to us, which is $6. Although it is not written as a fraction, it basically is like over 1 if you want to think about it that way. When you do dimensional analysis, opposites cancel. So you need to put the opposite unit in the opposite location. That means when we look at dollars, it's up on top, which means we need dollars on the bottom. So we would want to use this conversion factor here. This would be 100 pennies is $1. What we are actually doing here is we are multiplying everything that's on the top, and then we're dividing everything that's on the bottom, basically. So we would take 6 times 100 and divide it by 1, would give us 600 pennies that are left over. That is because these units will cancel out, because we are essentially taking dollars divided by dollars. They cancel just like if you took 2 divided by 2, it equals 1, right? Just like that. Units will cancel the same way when we do that. And this is how you should show your calculations, dimensional analysis way, with the units set up like this so that you see everything canceled, not just random numbers all over the place that's going to give me a headache as I try to figure out what the heck you are writing on that page. Yeah? So it does need to be an organized mess, not really a mess, but try to make it organized. And you do need to show dimensional analysis as you go through it. First off, any question on that setup there? Now, when we do something like this, in terms of significant figures, this is an equality, and this is considered an exact number. And when we have exact numbers in a calculation, we basically ignore them. So they have no effect on the significant figures of your answer. Exact numbers pretty much can have as many significant figures as you want. So, and when we have them involved in calculations, which is usually equalities, we ignore them, which means in most cases, if you're doing some type of conversion, it's a lot of times that original number has the correct number of significant figures that your answer should have. That original number has 1 significant figure. And did I do okay with my Sig Figs here? How many does this one have? It has 1 the way I wrote it, right? I would not want to put a decimal point here. Otherwise, it would have 3. And then we would be okay in that case. Now, there's lots of equalities that we commonly kind of come across in chemistry. You know, 1,000 milliliters is 1 liter. That's one we use a lot. A milliliter is the same as a cubic centimeter. Those are both volumes. A cubic centimeter is taken by length times width times height, which each of these measurements are length measurements, but when you multiply them together, you get a volume. That's a volume, and those are length measurements. In case you're in the healthcare, it's also a cc, which is a cubic centimeter as well. Give that guy 5 cc's of something before he dies. That is what that is. It's basically a milliliter as well. So those are some common ones we use. Not so much of this for us. We do see cubic centimeters like that, though. You know, we do see the 453.6 grams is 1 pound. That we see a lot. 1,000 kilograms. No, I did that wrong. Sorry. 1,000 grams is a kilogram. Let me get my eraser here. Try that again. There you go. I just did what I said don't do. There we go. 1,000 grams is a kilogram. We use a lot. Actually, coming up in the next couple of experiments, we'll use the one I had on the other page. 1 nanometer is 10 to the minus 9 meters. We see that one a lot as well. So each of these are conversion equalities, which you could write obviously 2 conversion factors for each of these. Now, when we talk about exact numbers and conversion factors and equalities, if you are dealing with an English to English conversion, like for example, 1 mile is 5,280 feet. That's sort of English to English conversion. That's considered an exact number. If you're doing a metric to metric conversion, where you're doing something like what I have up there, 1,000 milliliters is 1 liter, that is also considered an exact number. Typically speaking, though, if you sort of cross over from metric to English, they're considered really not exact numbers. Like 946 milliliters is 1 quart. Quart is English, milliliters is metric. You would need to look at the Sig Figs here. This would not be considered an exact number. The one you would look at is actually the Sig Figs that has a number. The other guy is usually a 1. You would look at the Sig Figs here when you're using that. The good news is, for the most part, even though you would look at something like this, a lot of times it's still that first number that has the smallest number of Sig Figs. So a lot of times you're still going to go off of that number. And like I said, in most cases, you probably would be pretty good. But technically speaking, if you cross over metric to English, you should look at the significant figures in that conversion factor. But if you have an English to English metric conversion or metric to metric, you don't have to worry about. The one exception would be this one. 1 inch is exactly 2.54 centimeters. So even though that's sort of a crossover one, it's exactly that one. So that's an exact measurement. So when we deal with calculations that involve these guys, for the most part, we ignore it unless technically you got like a English to metric one. You should take a look at it. Any questions on that there? So once again, if we had something like 2 types of units, all right? So if we had, I was driving, you know, a respectable 45 miles per hour, right? And I want to know how many kilometers, say, per second that was, right? I would approach this the same way. I would do really 2 conversions, right? I need to convert my top unit to kilometers. I need to convert my bottom unit to seconds. And this is really where dimensional analysis comes into play really well. So you could see where everything is. So for example, I would need something between, say, kilometers and miles. 1 kilometer, 0.621 miles. And hours and seconds, perhaps. You know, you could go, by the way, there are how many seconds in a minute? How many minutes in an hour? How many hours in a day? 24, not 60. Yeah, so sometimes people go 60, 60, 60. So 1 hour, by the way, is like 3,600 seconds. You could use that, or you could use 60, 60 if you like, which is the same. So if I were going to do this conversion, I would want to set it up dimensional analysis way, like so, where you could clearly see where all the units are. And when people don't do it this way and they just write like 45 miles / hours, they're not sure if they should be dividing by the number, not sure if they should be multiplying by the number, and they eventually will screw it up a lot of times. This way you could clearly see where everybody is. I need miles to get rid of, so miles needs to go on the bottom, so that would be 6.21 miles, and 1 kilometer would be on top. If I stop the calculation right now, the miles would cancel, and I would be in units of kilometers up on top and hours on the bottom. Now, you could absolutely get an answer at this point I personally would not round and then continue on with the calculation, or obviously you could just continue on with the calculation. And that's what I'm going to do. But because of the way I set it up here with dimensional analysis, I could clearly see hours are on the bottom, which means I need to put them on top, which is opposite. And that would be 1 hour is 3,600 seconds. The hours would cancel. The units I'm left with is kilometers on top, seconds on the bottom. And if I did this calculation here, we got 45 divided by 0.621 divided by 3,600 gets me something like 0.020128824 kilometers per second. That clearly is way too many numbers. Yes. So let's talk Sig Figs here. Basically, in this case, what we are doing is multiplying and then we're dividing, which means we should be looking at significant figures. This is pretty much an exact number, right? Because it's like, it's time to time, basically. This guy is kilometers to miles, which really we should look at, which is 3 sig figs. This guy is 3 sig figs, which means really we should end up at 3 significant figures, which is right about here. And we should end up with 0.0201. Again, here the units do not cancel, so we keep them both. Kilometers on the top there, seconds on the bottom. Typically, the number will stay with the top unit, and it's usually 1 of the bottom unit by itself. Any questions on that there? All right. Now, another type of conversion that sometimes people screw up on is one like this. If I had 43.5 cubic feet, and I want to know how many cubic inches that is, right? When you have a length measurement that is cubed, as we just talked about with cubic centimeters, it is actually a volume. So we're actually looking at volumes here, not lengths. So whenever you take like a length measurement and cube it, it is a volume that you're dealing with. So in this particular case, we could use the conversions between, feet and inches. And there are 12 inches in 1 foot, right? So if I were to do this, this is 43.5 cubic feet. Once again, we're going to go opposite here. So we want feet on the bottom, inches up on top. If I do this, did I properly cancel out everything? I did not. This is only 1, right? Which only takes out 1 of those. You're still left with 2. You actually have to do this conversion 3 times to get rid of all of the feet in this case. And if you do that, you end up with 43.5 times 12 times 12 times 12. Gets you on your calculator 75168 cubic inches. Inches times inches times inches. Sig fig wise, these are all exact numbers, which means original number had 3 sig figs. This guy should end up at 75200. I think, right? Cubic inches. I'll get to writing here. There we go. Obviously, you could also write in scientific notation, which would be 7.52 times 10 to the 1, 2, 3, 4 cubic inches. Here I dropped the zeros because if I put them in scientific notation, it would be 5 significant figures. That is 3 significant figures, no decimal here, 3 significant figures. So again, you could do it either way. Could you do it like this, 43.5 cubic feet, and do this? The answer is yes, but in my experience, people don't actually do the calculation 3 times. They just do it once, but they wrote 3 times, but they don't actually punch it in 3 times. So sometimes maybe just spreading it out there, you will hopefully see all the numbers and not forget to actually do that. That is a very common thing that people do. They forget to actually do the number, and sometimes they forget to actually square the units. Any questions on dimensional analysis or how to do these type of problems? One other side note of things that people commonly screw up on is how they put it into their calculator. We're basically multiplying everything that's on top, so you can put as many numbers as you want on top into your calculator. When you get to the end of the top, you should hit equals. And then for most people, they screw up because they have numbers on the bottom. They want to put them all in at once, and they don't use parentheses correctly. So if you don't want to run into that issue, you can always do it this way. As many numbers as you got on top, put them in, hit equals. Go to the first number on the bottom, divide it, hit equals, divided by the next number, hit equals, divided by the next number, hit equals. You will never screw up your calculation that way. If you try to put all those bottom numbers in at once, which is a very common mistake, and you don't do the parentheses right, you will oftentimes find yourself with the wrong number. And people go like, I have it set up right, but I don't know where that number came from. And again, it's more of a calculator sort of issue. Question on dimensional analysis are those type of things. You do need to show your work like this, yes, in dimensional analysis for things that are obviously dimensional analysis type of problems. Is your calculation should not just be random numbers on the page and things all over the place. So, all right, so that is that. Let us talk then about temperature conversions. There are 3 different temperature scales. There is the degrees Fahrenheit, there is the degrees Celsius, and there is our favorite here in chemistry, Kelvin. First difference between these guys is degrees Fahrenheit, degrees Celsius. It is just Kelvin. It is not, this by the way is Kelvin. There's not degrees Kelvin, so you don't use the degrees thing or anything like that. It's just the capital K. Some conversions here is the temperature in Fahrenheit is equal to 1.8. The temperature in Celsius plus a 32. The 1.8 is 9/5. You maybe learned that when you're younger. As a conversion, you could do that as well, but 1.8 times that. To go from Fahrenheit to Celsius, the temperature in Celsius would be the temperature in Fahrenheit minus a 32 divided by a 1.8. Truth be told, not so much happening here with these two. Occasionally they do come up and stuff like that, but we don't do a lot of degrees Fahrenheit or degrees Celsius here in chemistry. It is really this guy that we use a lot. And if we want the temperature in Kelvin, you take the temperature in Celsius plus a 273. The proper number is 273.15. Most people just round off the 0.15 anyways. So most people just use 273, but if you're fond of the 0.15, you can keep it if you like. That also means that if we want the temperature in Celsius, it would be the temperature in Kelvin minus a 273. I would say these are definitely the two that we use the most, and this one up here, probably the one that we use the most of all of them. Pretty much every single chemistry equation that you come across that has temperature involved, it needs to be in Kelvin. So that is definitely a. If you happen to be in Fahrenheit to begin with, you got to take it from Fahrenheit to Celsius, Celsius to Kelvin, and vice versa, obviously, if you're going the other way. Now, there is a specific rule that we follow for significant figures when we're dealing with temperature and only temperature, that if we are doing a conversion from one temperature value to the next, we basically make the converted number look like the original number. And what that means is if our original number was a whole number, when we convert it, we would convert it to a whole number. If our original temperature value went to the first decimal place, we would take our converted temperature to the first decimal place. The reason for that is it's really this number here. Some people use 1.8, some people use 1.80, some people use 9/5, you know, so a lot of variations. So it's a specific rule specifically for temperature sort of conversions. So if we had, say, 98.7 degrees Fahrenheit, and we want to know what that was in Celsius, we would put it into our equation, 98.7 minus a 32 divided by 1.8. I'm going to hope I picked the right number here. We'll see. So we'll take 98.7 minus a 32 divided by a 1.8. gives us on our calculator 37.0555, a bunch of fives. What we would do in this case is our original temperature went to 1 decimal place, so we would round this to 37.1 degrees Celsius in this particular case. So we would take it to the first decimal place in this particular case. So again, if we went to a whole number, you would just convert it to a whole number. 2 decimal places on your temperature, you convert it to 2 decimal places. You do need to know this one. And again, out of all of these, I would say probably the guys in the box, and the top guy in the box is the one that we would use the most in this class. Any questions on temperature conversions? Okay, so the last thing we're going to kind of review then is density. Make sure. Density is equal to the mass divided by the volume. And we can rearrange this in a few different ways. We can solve for volume. It would be the mass divided by the density. We also could solve for the mass, would be the volume times the density. Sometimes people like the DMV triangle to remember this. Everybody loves the DMV. Density is mass divided by volume. Volume is mass divided by density, and mass is volume times density in this particular case. Typical units for density for solids and liquids is grams per cubic centimeter or grams per milliliter. Again, a cubic centimeter and milliliter are the same. For gases, we actually see density values given in grams per liter, and we'll see that when we get to the gas chapter. But density of gases are usually in grams per liter. But solids and liquids are usually, these two guys are very common. If something is more dense than water, it will sink, right? If it is less dense than water, it will float. In general, the density of water, liquid water, is about 1 gram per milliliter. By the way, density does change with temperature. So as the temperature changes, so there's the density. But for the most part, any type of book problem or something like that, if you need like the density of water, 1 gram per mil is typically the value that you use, unless it's really specific. If we have liquids with different densities, right, they will separate out, right, by their densities. The most dense liquid would be which layer? The least dense would be the guy up on top. And, if you threw something like a solid in there and it just kind of stuck right there between those 2 layers, that means that that little circle is more dense than what's above it, right? But less dense than what's below it, right? So it gets stuck there in terms of its density. Units here typically don't cancel out. You could also treat density and do these type of problems like dimensional analysis problems. So if you are given the density of an object, you can, an object had a density of 0.785 grams per milliliter. You could use it like that, or you could flip it around and use it like this. The number stays with the grams. So, if you had something like 500 or 425 milliliters, you want to know how many grams that would be, you could times it by the density here, 0.785 grams per milliliter. Those guys cancel, and we would end up with, again on our calculator, 333.625 grams. Looking at Sig Figs, this is 3 Sig Figs. This guy is 3 Sig Figs, which means we should end up here, and we should end up at, not that, we should end up at 334 grams. It would be our mass. Any question on density? Yeah.